Okay, so hi everyone. Welcome to the multi-institutional AGN seminar series. My name is Vivian Yu, and I'm an AGN enthusiast based in UC Irvine. I'm one of the co-organizers of this seminar series. And today I have the pleasure to introduce not one, but two speakers, Drs. David Law and Travis Fischer. David received his undergrad degree from University of Virginia and his PhD from Caltech, which was when I started bugging David for help in all my classes. David was one of the best grad TAs in the department, seriously. Since then, he became a Hubble Fellow at UCLA and then a Dunlop Fellow at the University of Toronto. He's now an associate astronomer at Space Telescope and the lead instrument scientist for MIRI MRS on JWST. And he's also an expert on studying the evolution of galactic structure and stellar populations from the young universe to the present day using IFU techniques. Travis did his undergrad at the University of Wisconsin and his PhD at Georgia State. After that, he was an MPP fellow at NASA Goddard and a research scientist with the Catholic University of America and George Mason University at the U.S. Naval Observatory. He then joined ST as an ESA Aura astronomer, and Travis is an expert on AGN gas kinematics. I know that for a fact because we've co-authored a paper on AGN feedback together a few years ago. So today, David and Travis are going to tell us about AGN outflows in Stephan's quintet. So please take it away.
Okay, thank you. And let me see if I can share my screen again. And go to that and use...
In presenter mode.
Yep.
Looks good.
Nice. Sorry.
Okay. Great. Well, thank you for the invitation to talk to you today. What I wanted to talk a little bit about is some of the work that we've been doing looking at NGC 7319 and the AGN that's buried down at the bottom of one of the galaxies in Stephan's quintet. This is something you've probably seen a lot of the early work that we did on this already, because it was the component of some of what we were demonstrating as part of the JWST early release observations that we put out back in July to showcase the power and ability of the IFUs on JWST for the kinds of questions that we can answer now. So many of you are probably familiar with Stephan's quintet already, and I'll back up and say that I'm pronouncing it Stephan's quintet as opposed to Stephen's quintet. That's at least how I've heard it always referred to as. It's a series of interacting galaxies that's at a redshift of 0.0 a few. This is the central regions of Stephan's quintet itself. There's another galaxy that's kind of off the field in this view, but it's composed of these two systems down here, NGC 7318A and B, NGC 7319, which is the one that we're going to be interested in today, and NGC 7320 over here. Even though it looks like all four of these are interacting with one another, then this big one here is actually not part of the party. It is at a much lower redshift and just happens to be seen in projection in front of what's going on in all of the other galaxies. So this one's actually a factor of 4 or 5 closest. You can start to resolve individual stars, as opposed to the smooth distribution of starlight you get in all the others. So it's a very active environment where you've got lots of galaxies all merging together. They're tearing off long tidal streams of stars, and you get massive bridges of gas and dust and star formation occurring in this region between the galaxies here as well. That's not obvious in this image. This is one of the ERO release images from NIRCam that we put out that shows where the stars and the stellar populations are. Where it starts to get a lot more exciting, though, is when you look at what the MIRI image looks like. Here's what you get if you look at mid-infrared wavelengths. Now you can actually start to see what's going on with the gas in this system. So over here in this foreground galaxy, you're seeing the emission from the clumpy interstellar medium and the PAH type features. This green set of gas here isn't in any of the galaxies. This is molecular hydrogen emission that you're getting in this sort of bridge of tidal tail and interaction type features, along with triggered star formation over here. And what we're most interested in now is this bright red source right here down at the middle of NGC 7319. And that's the buried AGN, a type 2 CFIT that's sitting at the bottom of this galaxy that if you're looking in optical and near-infrared wavelengths, there's really no indication that it's there. But by the time you look out into mid-infrared, about 15 or 20 microns or so, this is becoming a super bright, very obvious source. And that's the AGN that we're interested in studying today. So we've known that the AGN was there for a number of years or so, now going back to the 80s or so. There have been studies of the radio lobe emission from this galaxy. But one of the nice papers from about 10 years or so that I'm familiar with is one that did optical IFU studies of the entire galaxy, just to put the AGN in context. So this is a couple of plots from a nice paper by Rodriguez-Barras and others in 2014, where they took the PPAC optical IFU, it's the same IFU that was used for the Khalifa survey, and studied the entirety of this galaxy and got resolved spectroscopy over the optical bandpass. And they made measurements of what you get for key emission line ratios. So one of the classic ways, of course, studying AGN, you can make measurements of things like the N2 to H alpha ratio, O3 to H beta, and see if those line ratios are consistent with photoionization, either by starlight, by the harder ionizing spectrum of an AGN, etc. And they really demonstrated that when you're looking down at the centers of this galaxy, then you've got these kinds of line ratios between N2 and H alpha that are really just inconsistent with photoionization by stars. They're really telling you there is an AGN buried down at the bottom of this galaxy, and it's contributing a large amount to the ionization budget of the gas down in those central regions. So what we're interested in doing with Webb, of course, is digging into that on kiloparsec scale and a sub-arc second level, so we can actually say something about what the structure of the AGN is and how it's actually influencing the galaxy around it. So there's a really nice diagram from a paper this year, actually, by Pereira Santaello, showing what the detailed structure on sort of few hundred parsec scales of this system is. We're talking about a AGN down at the bottom of the galaxy. It's got a two-lobed distribution for the flux that you see in most wavebands. It's got a northern lobe that's fairly nearby, a southern lobe which is offset by a larger amount, a few arc seconds or so down to the south. So a lot of the area that we'll be interested in trying to get information on is this northern lobe up here, which turns out to be quite complex, and a little bit of information on this southern lobe down here. And what you see in the ultraviolet, which is what we're looking at in this image, corresponds fairly closely to what you get when you look at radio continuum observations as well. So those are these contours drawn on top of it. And it's kind of tilted with respect to the line of sight. It's a little bit foreshortened along one axis. You can see the approaching outflow is this one on the bottom, and the receding one is the outflow on the top. So we thought this would be a great target for illustrating some of the power of the JWST IFUs for the early release observations we put out. So we targeted the central few kiloparsecs or so with both near-spec and MIRI, integral field spectroscopy. Loosely plop the IFUs over the center part of the galaxy and see what we see. We're not going to get much in the way of kinematic information from the near-spec observations, unfortunately. We use the R of 100 prism observations for this so that we could go kind of deep and just see what lines are there in the near-infrared. But for the mid-infrared, we've got spectroscopy at a high enough spectral resolution that we can actually start digging into the kinematics and say something about what the outflow velocities of this source are. But really, the aim is to just demonstrate the spatial and spectral resolution of the telescope and how deep we can go. So this is what we found when we looked at it with the MOS, and we could see a wealth of features popping up from the central regions of this AGN. So one of the things that's particularly exciting going forward is that we've got the kind of spectral resolution where you can see narrow emission features like all of these ionized gas lines. Now, those now stand out as super narrow features that you can do kinematic analyses of. You can measure the width, and it's not telling you about your instrument. It's actually telling you about the kinematics in the object itself. So you can measure the velocity dispersion of these lines and learn something about the kinematics of the system. In terms of the overall spectrum, then it's dominated by a fairly smooth continuum, as you'd expect for something that's generally quite so warm. So there's a large continuum increase as you go up to longer and longer wavelengths. You've got this dip in the spectrum around 10 microns or so, coming from a broad scale silicate absorption along the line of sight to the buried AGN. And then all of these features from various different kinds of ionized and other kinds of gas. So you've got low ionization features such as the argon 2 and 3 lines, higher ionization features such as neon 5, oxygen 4, and things that are coming from gas with remarkably high ionization potentials, things that have been ionized 4 or 5 times. So it's telling you that there's a lot of power coming off of the central AGN in order for it to be able to ionize the gas this far. We're also seeing a number of molecular hydrogen features in here, which is I find particularly exciting because it's something that's really new compared to what you get if you're looking at observations at shorter wavelengths. You can actually say where the molecular hydrogen is in this galaxy and how that's getting ionized by the blast of radiation from the central AGN outflowing through it. So one of the things that we did looking at all of this data is to start to say, you know, what's the morphology in all these various different lines? What can we learn about the distribution of gas in the system? And it turns out to be a little tricky actually to compare everything in a uniform way across the entire waveband. Is with near-spec plus MIRI together, we actually cover from about half a micron or so, all the way up to about 28 microns, which is an enormous range in the effective spatial resolution of the telescope. Down at the very shortest end at about 0.5, 0.6 microns or so, we pick up observations of ionized gas. So this plot in the middle, for instance, is a plot of H-alpha emission from this galaxy as seen with near-spec. And these are all continuum subtracted. So I've taken out the central point source, since otherwise in most cases it would just dominate the map that you're looking at. So the point source looks like this. I'm showing you the 4 micron image, just illustrative. You can see how it's not really just a bright central point source with the PSF petals around it that we're subtracting out. After you do that, you can see that the ionized gas has a strong column of emission up through that northern lobe. That northern lobe is certainly not a single knot, though. It's got a number of other sub-pieces in it as well. Now, ionization that's occurring when the outflow from the central AGN is powering through a molecular gas reservoir that seems to be around that central engine. That's what we see if we look over in this panel here. This is a plot of the molecular gas. This one's around 4.8 microns or so, one of those lines. And you can see not only the northern feature as well, but you can kind of start to see a ring of molecular gas that's around that central engine, even after you subtract off the emission from the point source itself. And what we think this is telling us is we're really detecting the gas that's fueling the AGN itself. A lot of the molecular gas that's ultimately descending onto the AGN and helping power these outflows is getting blasted through by the outflow coming off of the AGN itself. And you're starting to see these hot spots in the gas where it's getting ionized by that strong outflow. Similarly, if you look in the ionized gas at longer wavelengths, things like argon-2 and argon-5, that can tell you something about what the ionization state of the gas is. You can see that even out to the larger distances in this northern lobe, you're getting not only the low ionization lines, but also the higher ionization argon-5 lines as well. So the high ionization species aren't constrained to just the very central region around the black hole. They go out to a couple kiloparsecs or so out into those lobes. By the time you get out to 26 microns, the PSF is becoming huge. It's almost an arcsecond or so in size at these wavelengths, so it's hard to see much in the way of structure. But you can actually see O4 emission from all of these parts of the galaxy as well. And there's substructure in here as well that gets lost in the single map that I'm showing you here. There was something else that was in the original data that I was showing you. So if I step back a couple slides, remember that now there was the second knot down here, the southern knot. And we picked that up in the Webb data as well, but only at the very longest wavelengths. Because the Webb IFUs have a footprint that gets bigger as the wavelength increases, then the short wavelengths only cover this central region in here. The longer wavelengths pick up that southern feature as well. And we can start showing what that looks like with kinematic information too. So I'm attempting to show an animated image here, which I don't know how well that's going to work over Zoom, but hopefully you should start to see a shift in the emission. This is the wavelength domain that we're stepping through in this movie. So we're starting off blue shifted from the main AGN itself. You see this southern knot down here showing up in the oxygen 4 emission. It's offset by about 400 or 500 kilometers a second or so. As you shift into the central regions, you pick up the emission from both the area right around AGN and also this northern knot. And you can get some kind of idea that there's a little bit of structure in this northern knot as well. It's a little hard to tell with the large PSF, but it's not just a single blue shifted down here, red shifted up here. There's a substructure within it. So if we try making some plots of what the kinematics of that northern knot look like, they're actually quite complex. So this is zoomed out. The neon map that I'm showing you here is the equivalent of that moving animation I just showed you, where this is the blue blob down here for that blue shifted outflow in the southern knot. The northern knot is this one that has a combination of blue shifted and red shifted features. You can see those breaking down a bit better if you look in the argon lines. This is largely just because they're shorter wavelength and we've got better spatial resolution. And you can see that there's a complicated structure in here. It's not just a single outflow. There's a lot of substructure within the gas that the outflow itself is powering through, and you get both blue shifted and red shifted components from this gas. If you look at the molecular hydrogen, things are perhaps a little bit clearer. You can now see that sort of ring of molecular hydrogen around the central AGN. This is the reservoir helping fuel the AGN. And you can see possibly a rotational type signal in this. Possibly it's the molecular gas as it gets entrained in the outflow. It's a little bit more clear what's going on as opposed to having this multi-component kinematic structure to it. And this illustration that we put out with early ERO release is very hand-wavy in terms of exactly what the velocities of each of these components are. And there's a reason for that. It's because it was pretty difficult originally to say exactly what the velocities of each of the components were in the original analysis that we did for this. And the reason why is because when we were doing this analysis, we didn't actually have a wavelength calibration for the instrument at the time. So we were attempting to analyze this data at the same time that we were getting all of our observations to actually calibrate MIRI back in June. And so for a period of time, these observations of NGC 7319 actually defined the MRS wavelength solution for the long wavelengths. Because if you look out around 20 microns or so, then it's oftentimes quite hard to find much in the way of emission lines out there that you can calibrate on. Except when you're looking at something like a bright AGN, where there's well-known features like neon 5 and oxygen 4. So we could look at the AGN spectrum and see, well, I know what those two bright lines are, so this must be roughly what the wavelength calibration is. So for a period of time, the MRS wavelength calibration was actually tied to this AGN, which is very much not what you want to do. You don't want to calibrate a solution against a red-shifted AGN driving 100 kilometer a second outflows. But it worked as a bridge towards what we were doing later. Nonetheless, though, until a few weeks ago, there were still some issues with the wavelength calibration that prohibited us from really doing the kinds of analysis that we wanted to do. So looking at argon 5, for instance, here's what we had from the original data that we were looking at last month, where you see these two emission features around the wavelength you expect argon 5 to be, but it's not obvious what's going on there. Is it now a two-component outflow that you're seeing in different locations? And as we've continued to make improvements over the last few weeks or so, we found that that's now refined substantially so that you can actually see a single peak from the argon 5 emission feature, much more in line with what we'd expect. Similarly, if you're interested in studying the molecular emission in the galaxy, what used to be a double-horned profile that now differed from one side of the galaxy to another has now solidified into a single peak with a blue wing to it. So you can actually start doing a lot more kinematic analysis with this kind of data. I put one slide in here just to mention about how we're now actually very confident in the calibration accuracy that we've got for this data. There's an illustration from a paper we're in the middle of working on at the moment, for instance, just showing you the new calibration of the instrument against observations of a B-type emission line star. So all of these lines you're seeing in here are hydrogen emission lines around this star. And this is just an illustration to show that they all now line up at the correct locations that you would expect them to based on our understanding of physics. So we're now quite confident going forward that when we do further kinematic analyses, we can be fairly confident in those results. So this is the point in time when it tips over to Travis, really, because honestly, he's been the one leading all of the work that we've been doing at Space Telescope with this new calibration of data in the last few weeks or so. And that's part 2 of this presentation. I would be remiss, though, if I didn't also call out this lovely recent paper by Pereira Santaella and others. So they're part of the MIRI science team in Europe, who've also done a lovely analysis of some of the early maps of the emission line gas from this object. But in order to hear more about what's been going on in the last few weeks, I will turn over to you, Travis.
Cool. Sharing. Hey, all right, great. Hey, I'm Travis Fischer. I'm also at the Institute. I want to thank the presenters for asking David to come give a talk. And then David, thanks to David for asking me to help give that talk. So I To get into this a little bit for this analysis, I just wanted to give a little bit of context. So we had met, there was the early release data press release that was out, and then the next day, folks at the Institute had like a hack day in the cafeteria, and we're like, hey, let's all get together and try to see if anyone's interested in working on these projects. So I was down there working with the MIRI data, and David was there to provide the properly calibrated data cubes. So this is how this collaboration started, and I wanted to look at them because I'm very interested in, as David was already showing, that relationship between the ionized gas and the radio structure that we see in these AGN. So what we see in other nearby radio quiet AGN is that the narrowline region is consistently intertwined with the radio structures that we see in each one of these AGN. So you have in the green or red, no, I think they're all green, images, you have the O3 imaging here, and then in the blue contours, you can see the radio structure. And we are always seeing this alignment between the two different phases. And it's not just for this simple sample. If you look through any other papers, you're going to often see that you have an extended ionized gas structure in some sort of ionized state in iron 2, O3, O5, sulfur 3, and you're always going to have H alpha, you're always having the radio structure then aligned with the bright ionized gas that you're seeing in these host galaxies. And so what we're believing what that means then to us is that the extended narrowline region gas is the ionized surface of dense host material. All right, so we always see, again, then the relationship between molecular gas, the reservoirs of dust and gas that are in these host galaxies, and they are aligned with the narrowline region gas because that's the surface, that's the ionized surface of those reservoirs. And so the radio structure then is always aligned with the ionized gas. Together, that means the ionized gas is aligned with both the molecular gas and the radio structures, which then says that the radio structure has to always be aligned with the host galaxy. So if this was a radio jet happening in these radio quiet AGN, it would be highly unlikely that you're always seeing a radio jet oriented into the host plane of the galaxy. So we don't see that when we look at radio loud AGN. Radio loud AGN have these magnificent radio jets that are pouring radio plasma in these collimated pencil beams at relativistic speeds out hundreds of kiloparsecs into the circumgalactic medium. And we see that they're not correlated with the dense material in their host morphologies. So the hypothesis then that we've been running with is that winds produce these extranuclear radio continua that we see in radio quiet AGN. So as AGN winds are launched from small radii, they continue traveling outward and then collide with a host galaxy medium at larger radii. And when they have these collisions, they produce a shock. And when you have these shocks going off, they create these accelerated particles, which travel along magnetic field lines. And then that combination produces a local abundance of synchrotron radio emission. And then that synchrotron emission is similar to what we see in supernova remnants, right? So you see the same thing on a much smaller scale where you have these winds running into the surrounding medium, shocking it, and then producing the synchrotron lobe, if you will. So potentially what we're seeing then is the same thing on a much grander scale. And so when this data set came out, I was like, oh, that's very exciting. It'd be great to try to apply this hypothesis then to what's available. Here's free data, no information. I didn't know NGC 7319 beforehand. I was like, I'm just going to go look at it and see what's available. And so it had this MIRI data that was a plethora of different types of emission lines, which I'll show you. And so we just wanted to take a look at the kinematics that we could see in the ionized gas and in the molecular gas, and then compare that with any sort of extended radio structure that is there to see if it supports the provided hypothesis. So this is, David already showed, but this is the Stephan's Quintet, as I like to call it. And you can see that our target is up, NGC 7319 is in the upper left-hand corner. And so this is a near cam image of the 090 wide band And if we zoom in on that region, you can see that there's these magnificent dust lane structures that are surrounding the AGN. You can see that there's two kind of like a forking arc to the top, to the north, and then there's a very dense knot that's right next to the nucleus to the south of it. But these structures then are playing a key role then in the morphologies and the kinematics that we observe. So when we look at, this is the neon 5 line. So I chose a couple different lines to try to fit here and to show everybody today. And so this is neon 5, which is a very ionized line. The ionization potential is around 90 EV. So you definitely need an AGN to be frying this gas. And so when I did all of the fits here, I did a 2-component multi-component fit with 2 components, up to 2 components. So it either fit 0, 1, or 2 components at each individual spectrum, given the best fit. And so we can see that as David was showing in his that figure from that previous paper, the outflows are happening to the northeast, and the red-shifted outflows are happening to the northeast in component 1, and the blue-shifted outflows are happening into the southwest in component 1. So these are the bright, narrow components that are representing the reservoir that are being lit up and before they're being driven away. So what's really interesting then is that in component 2, if you're looking at where the radio structure is, we can see that red shift doesn't exist anymore, and there's actually a blue shifted structure there that's traveling around 200 kilometers per second, blue shifted, so toward our line of sight. So when you have this knot kind of running into, or sorry, the winds are kind of running into this reservoir, and they're splitting that gas into 2 separate directions. We can also see, so I realize that this is just a ton of data, so it's really hard to, and if you have any questions, if someone's moderating and could let me know any questions you might have about this. But if we're just focusing on where the radio structure is, which is the black contours over the data, you can see that the radio contours exist near the large full width at half max gas in component 2. And then again, there's also just that splitting going on. So the interpretation of what's happening here then is you have winds that are going red shifted, blue shifted toward from the nucleus. That's the bright gas in component 1. And as they're traveling outward, they're running into that lane that we can see from the continuum imaging and starting to split that. And then you have the majority of the red shifted outflows still working, but then there's a splatting. It's sort of a splitting happening here where you have a blue shifted wind that's pushed up away from the winds that are running into that lane. So we can also see that in the sulfur 4. So sulfur 4 is similar in ionization potential to oxygen 3. So if we were looking at oxygen 3 without any reddening, we might observe some similar kinematics. Again, the point here is that you have these blue shifted winds on top of the red shifted outflows to the north where all those dust lanes are, and we don't see that similar splitting action happening to the south. But again, you're seeing that high full width at half max gas in the sulfur 4 in component 2. So both of these are telling you the same story, that there's winds that are traveling outward radially along where the bright gas is, and then at greater distances you're seeing this splitting happening in the northern arc here. And then, so this is iron 2 measurements. And so iron 2 has an ionization potential of 7.9 EV, so it's really easy to produce. And so what we typically associate this emission line with is shocks that are occurring, and not necessarily an AGN ionization source. So we can see that the brightest part of the iron 2 emission here, then you can see in the flux map for component 1, is that it's co-located, and figure 2 or component 2, they're both co-located with where the radio knot is. So you've had the structure in this location is exhibiting the largest amount of shocks. And you can also see then, if you try to associate what the iron 2 emission with the continuum imaging, this should make sense, because this is where those dust lanes are. All right, so you're seeing the greatest amount of kinematics or morphology and then splitting happening where the winds are interacting with this dense host medium at that specific distance from the nucleus. And then we can also map the molecular gas. And then this traces the morphology and the kinematics of the gas outside the narrow line region. So we can see that the kinematics, excuse me, that you see in the ionized gas, in the shock ionized and in the AGN ionized gas, have similar kinematics to the molecular gas inside the narrow line region. However, that gas also follows those kinematics adjacent to the narrow line region, which suggests that all of that material was there intrinsically before the AGN turned on. So the reservoir that you're seeing wasn't like sculpted or pushed or anything by like a radio jet or any sort of and put out there to what we're seeing today. It was there before the AGN turned on, because you can trace smooth kinematics across the structure out from inside and outside where the narrow line region is. So this just shows that the structure that we're seeing is this material, this skin of these dust lanes that we're tracing in the continuum imaging. And we can see that this gas isn't, the full width at half max isn't as great here. We're not seeing that big dark blue reservoir in these measurements, which would suggest that it's farther in and not being impacted and showing the same shocking that's going on that we see in iron 2 and in the AGN ionized gas. So we can also use all of the different rotational states of the molecular hydrogen in MIRI observations to kind of give us an idea of where the temperature distributions are. So if we look at the higher energy ones, the S6 line, we can see that that's really localized to where the radio emission was and the iron 2 emission was. And so what that's saying then is that the highest temperature of the molecular gas that we're seeing is where that shock is going on, where you're having the winds that are running out into that dust lane and shocking it. And that's where we get the enhanced, the increased temperatures using this molecular hydrogen flux distribution. All right, oop, pop out to show folks, thanks. Okay, so all these measurements were made on a pixel to pixel basis. And so I just thought this was really helpful to point out to other folks that are doing IFU analysis, because I just had this conversation with David last week, and it would be helpful if everybody understood this potentially. But when you have your IFU data, so this is the MIRI data cube, and we're going on a pixel by pixel basis. You're going to see that when there's a point source in the field, the pixels produce this sort of ringing effect, which is just the worst when you're trying to fit it and understand the kinematics of what's going on in each of these individual pixels. And so David explained to me, and I'm going to repeat and hopefully say the correct things, but the PSF of the image at this particular waveband is much bigger than an individual pixel. So you aren't sampling it properly, and you're producing this fringing, this ringing effect. So if you sample the IFU, so I'm taking a circular aperture that's bigger than one single pixel with a radius of like 3 pixels, you can kind of see my aperture here now. If you go over all this emission line now all of that ringing is gone. And so what you're doing is you're kind of taking the average across all of these individual pixels that is about the size of the PSF of the beam at these wavelengths. And you can see that all of the fringing, the ringing is gone, and it's going to make it a lot easier for you to do your line analysis. So all of the analysis we've seen so far does not do that. So we need to definitely go back and try it this way as well to see if we can have a smoother continuum, an easier to subtract continuum. Because you get this staticky effect over any sort of PSF sources or some point sources in your data sets without it. So all of the different bands that or all the different emission lines that are available in MIRI just give this really cool consecutive image as we just go through that. You're going from the molecular hydrogen, you get to smaller and smaller reservoirs, and then you get the iron 2, and it starts to spread out again. Excuse me. And so together with all of these different wavelengths, you're really getting a full idea of the relationship between the molecular gas and the low ionization gas, the typically the optical, like the AGN ionized gas that we're used to, and then these coronal lines that we're seeing at like around 100 EV or something like that. And we can see how they're all related to one another. I'm just going to go through this video again. So this is the S1 line, the lowest energy molecular hydrogen line. And you can kind of see how the distribution of the hydrogen shrinks as we get to higher temperatures. And then we start to get where the shock happened, and then that radiation from the AGN is starting to hit this other distribution that is being funneled by where the position of those molecular gas reservoirs were. If we use the understanding then that the radio structure in these radio quiet AGN is a feedback process from the winds, we can use radio and all of the giant waveband coverage with MIRI to kind of create or finish a panchromatic atlas of radio feedback, in radio quiet AGN. So if you just start with like ALMA observations with like CO, and then you can go to molecular hydrogen, iron 2, then you have O3, this is X-ray, and then the radio structure here. You're starting from like the reservoir surrounding the AGN, and you're tracing everything as it begins to be, ignited by the AGN and then driven outward until it runs into something it can't drive out anymore and creates a shock and produces the radio structure that we see in that AGN. So if we just have that whole mindset, I think it really opens the door with understanding how important AGN feedback is to the host galaxy. Specifically, I think that you could use this then to create a sort of a survey of radio emission in radio quiet AGN. So then you can start trying to probe the incidence of when compacting potentially positive AGN feedback is occurring, right? So here's NGC 1068. You have the optical, the X-ray, opticals in green, X-rays in red, radios in blue. And if we just turn off the optical and the X-ray, you just have this radio structure, which is extended. And so if now you have some sort of signature that's showing that the AGN is running into the host material and compacting it at this region. So if you have a survey of AGN that you don't have any other wavebands in for, you can at least use the radio and see if it's extended to see if the AGN winds are doing anything to the host galaxy of significance. And so this could give us some sort of idea with models to say how often in our model should the AGN actually be doing something to the host, and they can incorporate this to have better evolutionary models. And then, here's some ideas of some galaxies that look like they potentially could be affected by some sort of positive feedback. You have non-isotropic or non-symmetric radio or stellar distributions. And so potentially this could be a byproduct of winds that are, again, compacting the gas at these large radii where you're no longer able to drive out gas, and that promotes star formation and producing the stellar distributions that we're seeing. So so just to take some stuff home real quick, MIRI data is amazing. As a nearby AGN astronomer, I want to use MIRI data all the time because it has just such a broad spectrum of signatures that are useful that it can tell you all sorts of things. And so just looking at NGC 7319, with the MIRI observations, we see that the radio structure is aligned with the gas outflows. It's co-located with the largest full width half max signatures we see in the ionized gas, and it's embedded in dust lanes as traced by the molecular gas. So these findings, again, support the hypothesis that the radio emission in radio quiet AGN is created by winds impacting a dense host medium at larger radii. This is like supernova remnants. And then the radio emission that you see is a byproduct. That radio jet, if it was a radio jet, had any choice to go in any direction, and it chose to run into the one lane that was like right next to it. So that's quite extraordinary that the radio jet decided to pick that very narrow lane in the very large space that it had to create that, deposit that radio knot if that was a jet. So so the observed radio emission then, I think, traces where gas is compacted, and that could enhance star formation and produce positive AGN feedback. And I would love if you have your favorite resolved AGN and you're not really sure how this applies to it, I'd love to sit down and try to take a look at it with you and see how it works. So that's it. Thanks so much.
Thank you, Travis and David, both for your wonderful talks. I think I see a question in the chat already, so I'm going to read that one first, and now call on folks who will have their hands lined up. So there was a question whether it could be a two-stage acceleration process in case if that is a jet, then the shocked gas could be re-accelerated by the ionization cone. I believe that's probably a question for Travis.
Okay, so the shocked gas was re-accelerated by the AGN the
Ionization
cone.
cone.
Right.
Mm-hmm.
But it's only that shocked gas is only located in the molecular hydrogen band that is happening right there. So so it would be, you're saying that the radio jet ionizes it, but then the winds are hitting it and then driving that gas away. That's the interpretation, I think. So it's weird then that it's that area is the only place with the high full width at half max gas. If that wind was hitting and blowing the gas away, you would expect to see it happening all along that radio or that molecular gas band, but you're only seeing the high full width at half max gas located where that shock, the iron 2 is happening. That's the only location where the high full width at half max is.
Great. Okay, so if there wasn't any more follow on that particular point, I'm going to call on Giacomo.
Yeah, hi, Travis and David. Very, very nice talk. Very interesting data and results. So I have a couple of questions to Travis. One is more on the interpretation of the data itself for the first galaxy you were showing. So basically, if I understand, you say that also the narrow component is tracing outflow. So basically, all the gas is in outflow, right?
No, so the narrow part is often the reservoir that you're looking at. So the narrow line is tracing like the dense molecular gas. And so that's often where the reservoir of the winds are traveling from. But you also see on top of that, a wind that is a high velocity wind that that is traveling outward. But the narrow line is not a wind. If a line is like 250 kilometers per second or narrower or something like that, that gas is just being lit up by the AGN. It's not being driven outward by the AGN.
Okay, so I thought I understood that you were saying that since you were seeing that red velocities to the northeast, that was outflow because it was a narrow component outflow, let's say, like shifted those velocities but not being in rotation. But yeah, maybe I misunderstood. Okay. And yeah, and then the second question was I didn't get how at the end you got rid of the fringes for the point sources in the pixel by pixel at the pixel by pixel level.
So I'm going to answer this, and then I want David to answer it more correctly. So what I did is, I mean, I'm using this tool. So right now, if you just look at a single pixel level, yeah, you get the fringing. And so what this aperture is doing is it's taking it's doing the average, or maybe the sum even, of all of these pixels here. But because yeah, the y-axis is much greater. What is it, 1800 here? And then, oops, sorry.
Yeah, it looks like you're summing over.
Yeah, it looks like you're summing them up, right? So, but I mean, when you do that, you're getting those, the fringes are canceling each other out. Like the waves are canceling each other out, and you're getting the smooth continuum then. So I think the idea would be to take this sum and then divide by the number of spaxels to get the spectrum at a given pixel. All right, David, what do you think?
So I'll back up and say that there's a number of issues of fringing and fringe-like signals that affect MRS data that you're going to see if you start digging into the data itself. The first is an intrinsic fringing that happens in the detector, in the sense that the detector has internal reflections that happen within it. So even absent anything to do with sampling, you're going to see large-scale fringe modulations throughout the entire milli-wavelength range, just because of effectively the detectors behaving kind of like a set of etalons with internal reflections that create this kind of effect. We take out a lot of that in the pipeline with a set of reference flats and also a secondary step where we model out the frequencies that you get from the detector spacing. But what Travis is showing here is kind of a secondary fringing, which has nothing to do with the actual detector absorption properties and is more to do with the sampling of the scene. The problem is, in order to have the biggest possible field of view for the IFUs, then the actual spatial sampling, how wide our slices are, how big our pixels are larger than you would want to if you wanted to actually Nyquist sample the point spread function that JWST delivers. So what this means, effectively half of Nyquist, you would want to have 2 samples per full width half max. Instead, at many wavelengths, we have 1 sample per full width half max. So as the trace from something narrow like a point source goes up the detector, as it changes between one pixel and another, you get very different sampling. When you then re-bin the native sampling of the detector into a regular cube, you end up with this kind of ringing structure because you are resampling undersampled data. And there's no good way around that. It's just simply a sampling artifact. But the best thing you can do to deal with it is to not look at spectra of individual spaxels. There's no information on that scale. The smallest scale you can get information out is the size of the point spread function. And if you go into smaller individual spaxel scales, then you'll see this ringing artifact the most. So as Travis is saying, if you're used to doing the kind of analysis where you do an analysis spaxel by spaxel through the image, one way to overcome this is essentially by doing a bin of stuff around each spaxel and then move that bin around the image instead. And that'll help mitigate this kind of a artifact near sharp features like point sources.
Okay, thanks. So if I understand correctly, all the maps that you were showing, so the values in each spaxel are given by actually taking the circular aperture centered on that spaxel.
No,
So
yeah, I didn't.
No.
I just did it on a spaxel by spaxel basis. And so you could see like that, how that really affected something.
Okay, so this is a workaround, a technique for future analysis. Basically.
That's right.
The one
That's
you're
right. So
proposing. Okay.
I definitely wanted everybody to know about that, because you can see from like my S1 line here, when I did the fitting, it just fits on top of that wavy continuum. So sometimes it under subtracted or over subtracted, and you get this like static that's going on, because you can see that there's a bright source that's near the nucleus at like S3 and S4 and S5. There's something down there that's bright, but it's too bright and it's too small and bright, so it creates like this PSF, and you get the waving, the ringing.
Yeah.
So it's not sampled correctly then. So that
Thanks.
But I had a pretty good time. I mean, the rest of it looks pretty good, like morphology wise. But I think I'd like to go back with this bin version to try the kinematics another time.
Yeah, I should add that when you're doing this binning, you're not really losing so much in the way of information, because there's a very large amount of covariance between adjacent spaxels in the data cube anyway. If you're interested in seeing more about it in detail, there's a paper I'm in the middle of finishing up at the moment, which talks about the origins of this effect and the degree of covariance between adjacent spaxels in the cubes and whatnot. So that'll provide more information.
Yeah.
Great, thank you. Dana?
Yeah, hello.
Hello.
Thank you very much for the talk. Very nice data. I just wanted to make sure if I understood correctly. When I have studied corona lines, no neon 5, but other ones that we have in the near infrared or in the optical, like iron lines or silicon lines, usually at the minute that I see nearby objects, at the minute I see the emission, the corona emission a bit extended, I mean, a bit away from the center. Usually coronal emission is very nuclear, but when you see extended, it's very hard to explain this emission with photoionization from the nucleus because the enormous ionization potential. So you had to resort to shocks. And I think is what you were saying, the coronal emission, I understand, must be, there's at least the part that is extended, not the nuclear, but extended, has to be associated with shocks, and these shocks presumably are induced by the passage of the radio jet. So I would expect the major correspondence between the jet components and the coronal emission, less with other lower ionization lines and the higher velocities. Is that what you see? The higher
so what you're saying is that you see a correspondence between the shocked gas and the radio structure, the extended radio structure, in all of these nearby AGN. And so, yeah, when you're seeing that those shock lines, I mean, those are these dense lanes that are really near. So like Markarian 573 has something like this. NGC 1068 has something like this, where you have a lane that's coming into the radiation field, a molecular gas lane or something, and it's rotating in, so it can't do anything. And that's where you're getting it's kind of like an immovable object meets the unstopping force. I don't know. But so that's where you're getting like these shocks then as you're driving it outward. So, I mean, yes, I totally agree that you see the radio structure there. But that means then again that the radio structure, the gas that you're seeing is in the host around the plane and around these molecular gas lanes, and that the radio structure then always has to be aligned with where these gas lanes are. So it would be fortuitous if it was a radio jet then always running into where these gas lanes are and shocking that material, and
it makes
somewhere else. That's right.
That I think it makes sense. No, the radio jet encounters some material and then excited, and you might have, among other things, the coronal emission. Okay. I think also that this double component that you see at certain locations, if I understood, was in the coronal emission as well. You have a blue shift and red shift component. Might be that you see the emission like diverted by you have by the plane of the sky. So some of the emission gets away from it, from the flow, the collimation of the jet, is some other come in the direction to us, because you are very close to the plane of the sky. As well.
I can't speak to I mean, I say coronal line. I don't really know if I should say that Neon 5 is a coronal line. I said it's coronal line because it's like 100 EV. So
yeah, it is, because it's not produced by stars. Yes. Yeah,
I mean, well, okay. So yeah, you have all of this really ionized gas, but I mean, you are also producing this Neon 5 in regions where there are no radio structures as well. So I can't say that it's necessarily affiliated with shocks, shocks at all, or it could just be photoionized. So my feeling is that it's still photoionized, but I would have to talk with my cloudy friends about that.
Great, thank you. And there was a question. I think Dashan, you had your hands up, and I guess you asked in the chat. Do you want to just ask it now?
Yeah, it was just a follow-up from the previous discussion, because what Travis showed was that there was a radius of 3 pixels to average out. And I was wondering that if you use a smaller radius, would you still see those wiggles, basically the fringing effects, if you use a smaller radius in that case?
I mean, so this is like this one, but if you change it to maybe go smaller. So here's like, yeah, like a smaller bin.
Yeah, you still see some effects, right? Okay.
Yeah, and you can still see some effects here at a smaller aperture that's happening. And so I went bigger here because this is on the red end. And so the aperture is very large here. I think that if you went on the bluer side of things, and well, even though you're still getting some sort of...
It's related to what the effective full width half max of the PSF is.
Yeah,
if you've got an aperture that is comparable to the PSF in size, it'll be fairly small if you've got good dithering. If you didn't dither your data, everything will be that much worse because you haven't filled in sample space as well.
Okay, good to know. Thanks.
Yeah, there's a couple examples in the figure for the paper I'm working on where it shows, this is a recommended width in order to make them go away, etc. So
yeah.
Great. I see a comment in the chat. Do you want to, we have a few more minutes if you want to say it? No? Okay. I was thinking I had a science question and I have an instrument question, and maybe I'll choose the easier one to go with first. Any updates on MRS? Is it coming back anytime soon?
I would hope that it is coming back online very soon, in the sense that people have now had a chance to study what's been going on fairly well the last few weeks. We think we have a better understanding of what's going on. There's a couple tests that we want to do first, but I'd hope that we're back in science operations fairly soon. NASA should be putting out a release with more information than I can publicly say now, hopefully fairly soon.
Okay, thanks. That's reassuring. I guess, Jeff, did you want to make an announcement? Just so you're...
Oh yeah, sure. Just any student who's interested in coming to the student discussion afterwards, I believe Travis will be joining us. I would put the Zoom link in the chat.
Great. Enrique?
Yeah, I have a technical question for David. So I think that you were mentioning that you were doing some PSF subtraction. Could you mention a little bit the details about what kind of PSF subtraction that you perform?
Yeah, for those plots, at least, it was a super simple PSF subtraction in the sense that we just found a adjacent continuum region of the spectrum, very near in wavelength space, and scaled that to be an appropriate estimate of if you interpolate the continuum from one side to the other of the emission line, take a continuum image from the other side, and just scale it slightly to where you expect the continuum to be at those wavelengths, and then subtract it off. We haven't tried doing anything more generalized for those images that I was showing.
Okay.
Dana, do you have another question, or did you just have your hand up still?
Oh, no.
Okay, thanks.
Okay, sorry, I didn't know it.
No worries. Does anyone else have more questions? And a reminder that Travis will be staying a little longer for science discussion. Shabita, do you have any more announcements?
No, just wanted to thank David and Travis for a wonderful talk, and also all of the amazing work that they've been doing to enable all this science for the whole community.
My pleasure. Thanks for the invitation to come talk to you.
Yeah, this was very useful, even though I've been looking at the data myself for the last 2 months. Yeah, so we're coming up to the hour. So yeah, let's thank David and Travis again. And then for any of you who would like to stay after to talk to Travis some more, then please stay on. Thanks everyone for being here.
Cheers.
Cheers.